keynote speaker, Professor Romain Serizel. Yeah, I hope I spoke it correctly. Yeah. So Professor Romain is associate professor in the Université de Lorraine. Yep. I'm trying. My French is not that good. In Nancy, France. Yes. Yeah. So thank you so much for being with us and for accepting our invitation. And please feel free to present yourself. Thank you.
Okay, great. Okay, hi. Well, thanks for the introduction and for the invitation. Before I start, just a small disclaimer, like my presentation might be a wee bit technical. I realized like I was expecting to be in front of a bunch of nerds like me, and it's, well, no offense, but that's not the case. Hopefully you still find it interesting. We are going to talk about monitoring the environmental impact of machine listening system. Well, why machine listening system? Because that's what I do. But that could be basically any AI system. And when I say that's what I do, well, it's not a one-man gig. So you have the name of the person who have been involved in this work. And what I'm going to present is mainly Constance and Francesca's work that you'll see today. But let's get started. So I guess I could even like skip this one. We've been talking about this like since this morning. So, well, but still, let's remind it, like we are working with AI system, and too rarely we are asking the question like, what is the footprint of a system? What is the cost of the performance, and what is the cost of the performance improvement we're seeking? And so the follow-up question is, okay, but if I want to know the footprint, how do I measure that? What kind of metrics do I have? Are these metrics reliable? And can I relate these metrics to the performance if I want to assess the cost of the performance improvement at some point? Well, then a second disclaimer, a scientific one here. So what we are going to do here in the presentation, we want to raise awareness and we want to compare models between each other. But we are not going to give absolute estimate of the energy consumption. And we are not also going to study the footprint at runtime, because these would require knowledge on the target devices, which we don't have. And as AI researcher, we spend, well, arguably, if you deploy an AI system, then most of the energy is spent at runtime. But as AI researcher, we also spend most of our time training some system. So it's important for us to start with to save energy when we are training systems. So that's why we are focusing on this during this presentation. And so I'm going to start with short presentation of the metrics we have at hand. Then we'll discuss about moving towards like a fair comparison of system. We'll discuss about energy and performance and the relationship. And finally, I'll present a small example of what we can do when we compare system and what we could conclude from the current way we are doing things. So, well, if we are considering system complexity, we can move to metrics that are easy to get, like runtime. So, well, I train my system, I just have to clock it, and I can get runtime. The problem is it's highly dependent on model implementation. It's highly dependent on the hardware I have at hand. So it's easy to get, but it's not so close to what I will get down the line in terms of carbon emission or footprint. The second aspect that is possibly a bit less dependent on the implementation and so on would be the number of parameters. That could be somehow related to the computational complexity. It's supported by most of the deep learning libraries. But each operation have different costs, and so the parameter does not translate directly to the cost of the model computation. So as we talk about operation, then we can count the number of operations that we need to run the model. This is still hardware independent. Well, this is hardware independent. It's nice. It's not trivial to compute. If you have a simple system, it's easy. If you start having like transformers and things like that, computing the number of operations is far from trivial. But it's bringing us closer to the energy footprint because this is the actual computation we are running. And a bit closer is the energy consumption. This is a good indicator of the potential footprint. The problem is that how can we monitor that if we have other jobs running on our computer? And also, if we want to use that at runtime, then we need to target a specific device, and this is going to be highly hardware dependent. And the ultimate goal would be to monitor carbon emission, because that's what is going to matter on the environmental side. It's related to energy consumption, but it also depends on the local electricity infrastructure, as pointed this morning. And so the problem with that is if we take the carbon emission, then it could lead to unfair comparison. Because remind that we want to compare models, and models that are trained from people all over the world. And we don't want to end up in a situation when people are training, let's say, the same model, but someone is training it here in Great Britain. And we'll have a certain carbon footprint. And the same person is going to train it in the Kosovo, and it will have like 4 times as much carbon footprint just because of the electricity mix. So you don't want to penalize people just because of the energetic mix of their country. So we're not going to use the carbon emission, but we are going to focus on the energy consumption, which is independent of that, to compare the system. Now, the problem is, as we've seen, we want to be fair in the comparison. We just want to compare the model. And once again, we don't want to compare the hardware people have at hand to run the system. So the question here is there an easy way to compare the energy consumption across different sites? So experiment running here in Surrey, experiment running in Nancy, experiment running in India, in Japan, in the US, and we want to be able to just compare the model, regardless of what hardware you are using. Oh, then the question is, which of the impact, which have the largest impact on the energy consumption? Is it the hardware I'm using, or is it the way I'm training, all the parameters I'm using, how much I use the hardware? And so we designed the first naive experiment. We decided to benchmark training of a system on several GPUs. So we have several GPUs on our cluster, several GPUs model on a cluster in Nancy. And so we decided to take one system, and that was the naive part. We were like, okay, if we do this study for one system, we can possibly extend it to something else. So one system, we don't care about like what's in there. What's important is maybe that there is 1 million parameter. What is more important is that we are using 6 types of GPUs from pretty old GTX 980 to 800. And we train this system until convergence. And as we want to assess the impact of the training parameter, one simple way was to change the batch size. And the assumption was that batch size is a good proxy to GPU use. We'll see that this is not so easy and obvious later on. So this is what we did. And then we realized, like during this experiment, that if we change the hardware, if I change the GPU, this can have a large impact of my consumption because of the training time and because of the GPU consumption, and because tasks are going to be more parallelized at some point or less. What we saw during this experiment is that increasing the batch size is going to have a minor impact, and we actually didn't see any significant impact on the batch size. So, well, this is what we saw, like if we take just 1 minute, then regardless of the batch size, there is no impact on the consumption, but there is an impact on the training time. So then overall, you might have an impact on the overall consumption. The hardware, on the other hand, have a large impact on the energy consumption per minute and also have a large impact on the training time. And so surprisingly or not so surprisingly, like big recent GPU are consuming much less and are much more efficient in training because they are faster and they are also more efficient. So first proposal regarding that was like, well, we normalize the energy consumption across the site. How do we do that? We give a reference system, the baseline we saw above, and everybody run that for a certain amount of epoch on their hardware. They give a number, and then we can just normalize according to this number. One assumption for this is that the batch size is a good proxy to measure the GPU use. And a second assumption that is related, like that could be somehow valid if the first assumption is valid, is that I just need one reference point to normalize. So after that, we did conduct some additional study. And the first one is my energy consumption independent from the GPU use? From the experiment we did with the batch size, it seems so. But is it really the case? And so what we did then is take much simpler system. We took a bunch of CNN, of RNN, and of MLPs, and then varied the parameters of this system, which we couldn't do with the more complex system. And here we increased the parameters of the system until we reach full occupancy of the GPU. And for each of these configurations, we did monitor the energy consumption. And what we saw is that, well, the consumption is not, well, it's not so surprising, but it means that the batch size was not a good proxy. And so the energy consumption does depend on the GPU use. It's not surprising. What is bad news for us is that there is not even a linear relationship. If there was a linear relationship, then it's easy and we can fall back to our one reference point. Now, with this type of relationship, and we don't even know if there is a way to model that, then it's getting a bit more difficult to say, okay, I can normalize with 1 point. Next question is, okay, let's see, maybe we're lucky. And if we just take 1 point, it's work. So that's what we tried. We did the same experiments, so took the same CNN, RNN, and MLPs, this time running on several GPUs, and monitor the energy. And so what we try to do is find a linear mapping between the energy on both of the GPUs. So what we have on the top left here is no normalization. So we see that depending on the hardware, we are pretty far from the linear relationship. So we need a normalization. Then what we see on the right and on the bottom left is when I take only 1 point. So I take like a point with low energy or a point with high energy. We see that it's working in the area of the same energy consumption. If you go away, it's not working so well. So the idea is, okay, then I take 2 points to do my linear regression. And it should work. I take 1 in the bottom, 1 in the top, and well, it's working. I mean, I'm making less error in the consumption, and I could normalize my consumption and compare the system fairly, because that's the goal in the end. Well, does not always work well. If I change the hardware I'm using, then it seems that even with 2 points, I cannot normalize. So I cannot find a linear relation between the consumption in the two on the two hardware, which is making my life much more difficult if I want to compare the systems. So the idea is that I don't have a linear relationship between the energy consumption on the two hardware. So I'm looking at the 2D space, and it's not linear. What happens if I expand the space? I go to a 3D space or 4D space. So I'm going to add another axis or 2 other axes. Those axes are the metrics we talked about earlier. So I'm going to take the number of operations or the number of parameters. Just a side note, we did also try to use other regression because it's not linear, but we did try like support vector regression and polynomial regression. And we did also try adding more reference points, but it was not changing so much. And this idea sounds a bit cooler than just changing the regression. And so how, well, does it work? Yeah, it works. No, you don't see it on this 3D plot? Well, so basically we see the idea now. Before we had at least the 2 hardware consumption, and we were in the 2D space, and now we're adding, like on this case, the flops. So we have a 3D space, and then it's potentially easier to fit an hyperplane here than just an hyperplane in the 2D space. So, well, I know that this one is not convincing, but we did try like computing the mean square error between all my points and the hyperplane. And what we see, the red one on the left, happened in the 2D space. Then the pink one is what happened if I had the flops. The purple one is what happened if I had the number of parameters, and the brown one is what happened if I am in a 4D space. And what you can see is, regardless of the hardware pair, if we are in the 4D space, then we manage to find the hyperplane where we can relate between everything. Then what is surprising and what we don't understand quite yet is that depending on the hardware pair, then adding the flops can help or not. And adding the parameter, the number parameter alone is usually not helping. And this is potentially, but this is something, this is really an hypothesis. This is potentially related to the way the GPUs are working. But, well, I mean, it's fine. We found a way to normalize, an easy way to normalize the energy consumption. The only problem is that we cannot do this with 1 point. We cannot do this with 2 points. If we are working in the 4D space, then we need 4 points to normalize. But still, that's a nice thing that we found a way. And so for now, we'll assume that we can compare the energy consumption. And well, down the line, if we are training systems, is that we want them to do something. So we cannot just compare the energy consumption, and we want to compare this with the performance. And so how do I trade off between the efficiency and the accuracy? There is this common view that if I'm increasing accuracy, I'm going to decrease efficiency. And vice versa, if I increase efficiency, it would be at the cost of accuracy. Well, is it that simple? That's something we probably want to check. And also, how can I combine this? So we had a naive approach that we did try, which was like somehow we are going to combine the accuracy and the efficiency. So the really naive approach was just to have a product of them that you can weight, that you can have a, for example, a logarithmic weight on the efficiency, for example. And so this means that I have my reference energy and the system energy. If my system energy is larger than my reference energy, then the score is going down, and vice versa. If my reference energy is smaller than the system energy, then the score is going up. Well, the problem we noticed is that this was largely dominated by the efficiency. And we had a really problem like seeing any difference in accuracy if there were like large change of efficiency, which is nice if your focus is on efficiency, not so much if you're on accuracy. Another approach is to say, okay, I cannot do with one single metric. So let's keep the accuracy and let's keep the efficiency. And what I'm going to look at, I'm going to try several configurations and several systems. And what I'm interested in is those systems that are at the boundaries and that are the best in terms of accuracy or efficiency. And then I can know that probably I'm not interested in this black point anymore. Point I'm interested in are those red points on the Pareto frontier. If you want to know more about that, you can also read the paper from Constance last year at ICASP. Yep, I'll do that. So now let's go to the point like we've been talking about ideas, a bit of experiments. Let's get to the point where we try to put this at hand. And so we're going to work on sound event detection. So as all of you might not be familiar with sound event detection, what is it? I have a recording, I don't know, a few seconds long recording. There are some things happening. So there are people walking, people speaking, a car passing by. I want to know what is happening, but I want to know also when it's happening. Why did we do experiments on this? It's because we are running a task in the DCase challenge. So for those of you who are not working in audio, DCase challenge is something that you don't know. You don't need to know much about that. It's just a competition that is running every year. And with this, we have the opportunity, we have usually 20 teams participating to the sound event detection task. And so we get about like 100 different systems submitted. So we ask participants to report their energy consumption. So this means that we can have a study of energy consumption on a single task over 100 systems, which we could not do by yourself. So, I mean, it's easier and you have a larger variety. So that's what is interesting here. And so last year, we had like 123 submissions. We did the full study on about 100 systems, but what I'm going to present here in the interest of time is part of the study only on the best 15 systems. And so what we did is try to analyze the relation between the energy consumption and the sound event detection metrics. So what you need to know about the sound event detection metrics here, you'll see them later on, is just that the higher is the better. We don't care about how they computed or not, because we just care about like how they are going to matter in the graph. And the problem is that this was done last year, and the study about like how to normalize is something like which is pretty new, which is currently under review. So everything that we are going to see is normalized with a single point. So it's to be taken with a grain of salt, but still it's giving some pretty interesting indication of what is going on when people are working on different systems. And so if we take the best 15 systems, so we have energy at training and energy at test. Let's focus on the one on the left-hand side. On the y-axis, you have like the energy that is spent, and on the x-axis, you have the performance. So the further we go to the right, the best the system is. And what is interesting here is that we don't have like a curve or something. We have like pretty good systems here that are spending much less energy than systems here. And the performance gap is not so large here. So that was good news for us, because we were like, okay, people are doing like huge system because it's better. And so it's hopeless, like we cannot reduce. Well, we see that it's not really the case. And we see also, if we consider the Pareto frontier here, that we have a system, and even the most consuming systems are not even on the Pareto frontier. So they're not even like candidates for a good trade-off between accuracy and energy consumption. So, well, that was good news. First good news. Then the question we asked was like, okay, but people were totally free to propose the wildest system ever. What happens if we put an energy cap? No. Oh, okay. What happens if we put an energy cap? What happens if we say, okay, we can just keep like, well, the 25th percentile of energy? Or what if we limit the energy consumption to the median energy consumption of all the submitted systems? And the same goes for the 75th percentile. And so we wanted to see, like, overall, over 100 systems, would this really degrade the performance? Well, short answer is not really. I mean, if we look here, if we look at complexity, then the performance is not changing at all. If we look at the energy here, like, so here is for single systems. I have one system, then putting an energy cap and saying that I want really low energy, because going here from most complex system is 1 billion parameter to 5 million parameter, we're losing like 4% in terms of performance. And if we go from 1 billion to 11 million parameter, then we're losing nothing in terms of performance. If you take the ensembling system, so people are putting together like more and more complex systems, then the performance drop is even lower. So, well, I mean, that's a good news in some sort. It means that we could reduce the energy and still achieve the performance. The bad news is that if we just look at the performance, then we are spending a large amount of energy on and computation to increase the performance only marginally. Because we are just looking at this number and we're like, oh, okay, 0.1% more, I'm the best. Yeah, but you've been spending like twice or 10 times as much energy. And down the line, it doesn't matter so much. And if you were reducing, then you'd be performing more or less the same. In the same area. I have a bonus question here. If we take back the initial study, the one with the one system we trained on the six GPUs, and we trained it until convergence according to some criteria. Well, then the question we asked was, when should we stop training? I mean, my convergence is not something linear. My convergence is more something like this. And then we realized that we spend half of the energy increasing the final performance by 5 relative %. So, I mean, we could have stopped like much earlier. And I don't say that this is true for all the systems, but in general, like what we've seen on the baseline is what you see on many systems. So, to wrap up, if we want to compare like the footprint of the system, we have many complementary metrics. One is not enough. And we see that one is not giving like a proper view of the systems. And even if we want to normalize the system footprint, then one is not enough. We've seen that if we want to compare across site, there is many shortcomings in the way we are doing things, and we should be really careful before drawing any conclusion. And so this means also that we need somehow to standardize the procedure. Like just asking people to say, oh, just run code carbon and put the numbers is not going to lead us anywhere because we don't know what is behind these numbers. So then the second aspect is even if we know how to do that, then we need to find a way in which we could compare system in terms of both the footprint and the performance. And this is not going, there's not going to be a universal way. There is going to be a balance between both criteria, and this is probably going to be driven by the application needs. I don't need the same accuracy, or I don't need the same, I don't have the same energy consumption constraint depending on what I want to do. And the last question that seems maybe like a bit more trivial, but which is to me like maybe the most important and the most difficult to address is, how do we make this attractive to the community? How do we make people want to report the energy consumption? Because this is what is important. If there are just like 2 or 3% doing it, then it doesn't matter at all. And well, to finish on what could we do, then I think we should steer away from the simple like performance comparison, like, and question or practice and say like, okay, what is the worst improvement? Was it really worth to spend that energy? And define the cost that we are ready to pay for this improvement, depending on the application we are running. Thank you for your attention, and I'll try to answer your questions.
And thanks, Romain, for your great presentation. So we have time for questions. Yes, please.
Thank you. Really nice talk. Really interesting. So in terms of a takeaway from it, if you want to build a model that's efficient, in my mind, the takeaway seems to be use as little of the GPU as possible. Is that the wrong takeaway? And is there a better approach?
Well, that's not the only one. Because, okay. We did a study, like it's going to depend on the architecture of the model. We did a study that I'm not presenting here, that was like before, that was leading to this. Where was it? Yeah. That was leading to this. And so we did compare like all the architecture differently and trying to see like, okay, if I increase the number of parameters or if I increase the number of operation, is it increasing the consumption the same? And it's not. And this was with really simple models. So already with that, it's changing quite a lot. And so if you're going to change, have like more complex architecture and so on, it means that it's not that easy to say, okay, this one is going to be efficient. You probably should monitor it.
Yes, but maybe I don't understand, because on the last slide with the performance, that plot you just showed, you kind of suggested that it didn't matter on the model, whether it's CNN or RNN, it's following the same training. Is there something?
Oh, the relation between the use and yeah, but then finding like those points.
Yeah. Oh, okay, see.
Okay,
Right,
so
I see,
I'm
yeah.
designing my CNN. I know that I have that many parameters in my CNN. I might be like, I have 1 million parameters in my CNN, I might be here. I have 1 million parameters in my RNN, I might be here. Well, actually, that's probably the other way around.
So then it comes down to you've got to know how the GPU is allocated resources. Okay. Good, thank you.
Hi, thank you so much. What a great presentation. I was just wondering towards the end, so are we actually saying from a sustainability perspective that the ensemble models, they are kind of doomed because we are obviously training many, many more models to get small increases in performance? And also just extending from there, how do you see the landscape for these models changing based on energy consumption?
So that was a question we asked, and like we had those curves. I'm not presenting them, but we had those curves with with and without ensemble. And if you take those systems and you do ensembles, then we are doomed. But then at some point, we were like, okay, but what if I do ensemble on this system? And maybe I can get like for this energy increase to something that is like this one. And we were like, but participants didn't do that. So that was pure speculation. But we were like, maybe having more simple system is going to be more energy efficient than having like one more complex system. But this is something we should have tried or something, but that's beyond the scope of this. But when we were looking, comparing like ensemble and non-ensemble, we were like, okay, but maybe there is something here. Maybe the efficient way is not to try to find like the best system that is going to be like in the sweet spot here, but maybe like having simplistic system and having like 5 or 10 of them is going to be like a good way to find like an efficient trade-off.
Some of the energy goes on training the model,
Yep.
but then if you then deploy it, the energy goes on running the model. We had some discussion about edge devices earlier on, and if you've got edge devices, you've got potentially millions of these things running on there. So, what is it possible in some situations the training cost is actually the least important thing because you only do that once, and then the rest of it really goes into the deployment?
Yeah, if you're releasing a product, that's most often the case. We didn't focus on that for 2 reasons. The first reason is that if you want to do something at deployment, you need to know your target device because it's going to be like the energy consumption is going to be like hardware dependent. And us in the lab, don't know. We have no clue about the target device. So we could try doing something, but that would just be like, oh, okay. So down the line, that's what should be done. Like I have this application, it's going to be on this target, and so I'm monitoring what's happening when I deploy the system. So that was like, it was not feasible for us, and we don't know like the hardware side enough to run that type of experiment. The second justification was that as AI researcher, not working for company, but for academia, we do spend most of our time doing training. And so it's important still for us and for the community to say, okay, it's not because it's going to spend a lot of energy if the system is going to be deployed. Most of the systems we are training are actually never going to be deployed. So in our activity, most of the energy is on training. So, and it's important that if we want to bring the message that it's important to monitor the energy consumption, it's important to convince people in the community.
Can I be controversial and wonder whether it's worth worrying about these small amounts of energy when we're sitting in rooms with hundreds of watts of lighting and air conditioning? Are we really building enough models and deploying enough models that it's going to be significant unless we're doing large LLMs?
Well, I mean, like even here already, like, so this system normalized, it was like, I think 250 kilowatt hours to train one system. So 250 kilowatt hours with my electric car, I'm driving like 2,000 kilometers. This is to train one system. So to end up with this system, the participant probably like train 10, 20. So we're talking already about like 20,000, 40,000 kilometers with a car. I mean, I know that there is energy consumption everywhere else, but this is not like just a grain of sand. This is something that matters. Like it's still a substantial amount of energy we are spending here.
Okay, so it's fantastic that at the case in this task you have the requirement to report the energy consumption, and I believe as a community that should be like we should have a metric that is accepted by the community in general, in my opinion, because at the end of the day, when you submit a paper and you don't get the state-of-the-art results, it's very difficult to get accepted sometimes. Whereas if you have a metric that is accepted, that is a compromise between energy efficiency and accuracy. You can say like my system is the new state of the art in terms, like if you look at the black dots over there, probably so the state of the art there is probably one of the top of the on the top, whereas it's way more efficient, one of the bottom right dots, right? Whereas if you have a metric that can summarize both accuracy and efficiency, it will be fantastic.
Yeah, I do agree. That's why we are working on that. But right now, I'm not confident enough in the measure we get and in the way we can compare the energy consumption across sites to say, oh, you should report this. Because I don't know what's behind that. And there are plenty of stuff that we didn't discuss, like if we look at the GPU consumption, then something like code carbon is pretty accurate, but then everything else is, depending on the hardware, estimated or computed from some other measurement and so on. And so it's going to vary quite a lot. And so you cannot say, oh, you should report this, but I know that this is not so reliable.
I just wanted to ask, because the EU AI Act is actually bringing energy efficiency requirements, and also the new eco-design revision is requiring eco-design to address energy demands of AI. So I just wondered if you're aware of that kind of going to be impacting the community of AI users in the EU, because it's a big part of member states meeting their climate change targets under the European Climate Change Act.
Yeah, but can I be controversial here? I mean, there is what is done by the politician or something. They might not know technically how we can do or measure that, and so.
But that would.
So then it's a thing to say that, well, it should be monitored and we should do something to reduce it.
Where your techniques will come in, because it's like, this is the way we get accurate measurements that we can compare.
Yeah.
And,
but
it will inform the standards, so we should think.
It's important, but as I said before, I don't see this as ready enough to tell people, oh, you should rely on this metric this way to compare your system. There are too many uncertainties in the way we are computing this across sites and so on to rely on that and to tell people, oh, you're not making enough effort in reducing. So that's, but I do agree with you. It's important, but technically, I don't see how you can enforce this right now. From a scientific perspective, I wouldn't feel like confident telling people, oh, you should this metric and rely on this metric to.
So, Romain, thank you so much
Thanks.
for presentation.